Hey, my name is Charlie, and you can also call me the guitar boy. Today we are going to be discussing chemistry, and the topic we are going to be discussing today is relative masses of chemical substances. Under this topic, I decided to divide the topic on my own into smaller units so that I will not forget some serious points you are supposed to know as a chemist. So first of all, first thing I'm going to be doing, I will explain the meaning of relative mass (ROM). I will explain the meaning of relative mass (ROM). Then talk about mass spectrometer and isotopy. Mass spectrometer slash isotopy. Then talk about something to use something to illustrate the the concept of relative mass. I will use something. You are going to see how I'm going to use something to illustrate the concept. Then we also talk about relative mass slash Avogadro's number. Then we'll talk about carbon as the new standard for measuring relative mass. Then the last one, the most masses you see today are relative masses, not actually the mass of one unit of that substance. They are actually relative masses. Now, we'll start from the first one. What is relative? What do you understand? How do you explain the concept of relative mass? Now, in early days, our early scientists find it difficult to measure the masses of substances because they are very, very small. They are very, very small. They find it difficult to measure the masses of substances. What they now do, they have to now measure the masses of substances relatively with one another. Hence the word relative mass. Now, in that case, what they did was that the hydrogen, being the lightest element, was assigned a value of 1. The reason being that they want every masses of substance to be 1 and above, so that nothing will be 0.9, 0.4, 0. No, they want every masses to be 1 and above. So that if hydrogen is 1, helium will be more than 1. The other one will be more than 1, just like that, up according to the actual masses of a unit of the substance. The 1 unit, what's the actual masses? So, what's the actual mass of that unit? So, according to the actual mass of that unit, you now assign value to all of them relatively to that of hydrogen. So hydrogen was the lightest and was a reference point from which other substances were measured. So now, today, it is not very much possible to measure the actual masses of substances like before. The masses of substances were difficult to measure because they are very small. Which instrument will you use to measure them? Which instrument? But today we cannot use mass spectrometer to measure the masses of substances around us today. For instance, using mass spectrometers, we now know today that the mass of 1 atom of hydrogen is 1.67 times 10 raised to power minus 24. Mass of carbon is 1.99 times 10 raised to power minus 23. Mass of oxygen, this one is hydrogen, this one is carbon, this one is oxygen. Mass of oxygen is 2.66 times 10 raised to power minus 23. These are the actual mass, the real mass of 1 atom of these various substances. That is, 1 atom of hydrogen has the actual mass of this. 1 atom of carbon has the actual mass of this. 1 atom of oxygen has the actual mass of this. You see, as you can see, how small these masses of each unit are. Which instrument we would have used to measure this before the advent of these mass spectrometer we cannot use today to measure the masses, the actual masses of substances. But because these masses today are still very, very small, it is not also comfortable to use today. Imagine I want to do calculation in chemistry today. Imagine using this value. I will use for carbon, use for hydrogen, everything will be messed up. It will be very, very inconvenient to use. Hence, we still keep the use of relative masses. We still relate masses to by measuring them with making hydrogen the reference. So that's how they used it in the early days. But today we don't use hydrogen as reference. However, we now use carbon as reference. I'm going to explain that. Then from carbon, using hydrogen first, I will move to carbon, then conclude from there. So we have explained the meaning of relative masses. We have explained the meaning of let's talk about mass spectrometer. Okay, we have talked about mass spectrometer, that mass spectrometer helps us to calculate the actual masses of substance today. Also, mass spectrometer helps us to be able to know the concept of isotopy today. Isotopy is a phenomenon in which an atoms having the same proton number and having the same different neutron number. And as a result, you know that if neutron number is different, the mass number will be different of the atoms will be different. So that is the concept of isotopy. When we enter atomic structure, I will explain in details the meaning of what isotopy. So that's for that. Chlorine has two isotopes. Chlorine 35, which is 75%. 75% abundance. Then chlorine 25%. Chlorine 37 has 25% abundance, which means whenever you have chlorine, you have this. Whenever you have chlorine with you, these two types are always together. So whenever you have chlorine with you, these two types of chlorine are always there. They are always there together as isotope. So that's what this one actually means. So we'll talk about isotopy later. When we talk about atomic structure. Now, the next one we are going to be talking about is something to illustrate the meaning of relative mass. Now, I have explained the meaning of relative mass before. Now, you might not actually understand. Let me use something to illustrate it. I believe now it will be clearer for you to understand. Now, let's assume. Let's say you are the manager of a company. You have 3 workers under you. Let's say this is one worker. Let's call this worker hydrogen. This is human being, but I want to give it a name. I can give it any name. It's my concern. So this is hydrogen. You can arrest me anyways. This is hydrogen. Then let's say this one is carbon. This is another person, carbon. This one is another person, oxygen. Now, as all of them, this one is oxygen, this one is carbon, this one is hydrogen. All of them, the way all of them are arranged, okay, even in real life company, all of them might have different values. Their actual values, they might have different actual value. Let's say this one is the actual value of this one. Like when you ask somebody, what value do you have to contribute to this company? Let's say the actual value of this one is what? 1. Okay, the actual value of this one of this man carbon is 2. The actual value of this man oxygen is what? 3. So if these are the actual value of them, maybe for one reason, because the reason I gave to you, the reason why we use relative mass was because those atoms were very small. So we need something we can actually work with. Okay? We needed something we can actually work with. That was why we use relative masses. Now, let's say for any reason, maybe the manager, visitor now come to this company and now ask the manager, here are your staffs, I want to see your staff. And he now sees this man, hydrogen, he now asks the manager, what is the value of this man since he has been with you in this company? Can you just rate him? What is the value of this man? And in recent, the manager had done that before now. But it's just the manager is now for any reason want to help his company, like want to show to the visitors that yes, this man has a good value. The manager will just assign value to this guy. You see, the man has a value of 4. Okay, this man that has a value of this one is now having a value of 4. How is this man? How did he change to 4? This man has a value of 1. He's not changing to 4. How? So this man just maybe he wants to show that my company has good my company has good workers with good values, just assign a value to that. So now the manager, the smart manager would think that, oh, they might still ask me about the value of these ones, because this one that was having when I gave it for. Now, will I now tell them about the value of this one, the value of this one? So I have to give them another value comparatively with what they were having before, using this first one as a standard, as a reference point. Now, how do you now calculate the value of this particular one? Which value will you now? Because he's now expecting that this visitor will still ask him about the value of this one. He's not going to tell the visitor that the value of this one is 2. Look at what will now happen. The manager will say, if you understand proportion in mathematics, this what I'm saying now will be easy for you. Though it will still be easy, I will just make it simple. Now the manager will say, oh, okay, if I give hydrogen, this man hydrogen that was having 1, I gave it 4. What will I now give to this man that is not having 2? S, let me call S. S is what you don't know. I don't know. I will give this man that is having 2 S. S, I don't know. So what will now be S? You will now solve for S. How do you now solve for S? You now say, this S, this thing you want to calculate now, you want to know what you will give to this one, you bring it out first. You say equal to, you see what is here now? Everything in this cross, they are complete. There is no unknown, but here there is unknown. So what you have here, you now say 2 times 4 all over 1. When you do that, you now say 2 times 4, 8. 8 divided by 1, it will still remain 8. So the manager will quickly tell the visitors that this one has a value of what? 8. So the manager also in his head will also quickly calculate and say, oh, which value will I tell this person or that this other person? He will still follow the same process. He will say, okay, this one, if with reference, everything is with the first man. They are referencing everything to this first man, because it is this first man that caused the whole issue. So since it was this first man that caused the whole issue, so he's the reference point. We are going to measure everything relatively to this man. So you will not say, if this man that had 1 was not giving 4. Therefore, this man that has 3 will not be giving S. So when you cross, S will not be equal to 3 times 4 times 4 all over 1, which is equal to 12. 3 times 4 all over 1, which is equal to 12. So this one is now equal to what? 12. So the manager now cannot tell this visitor, or maybe this inspector, that, oh, this one has the value of 4, is a very good man. This one has the value of 8, is a very good man. This one has the value of 12. This is relative masses. So these masses were measured relatively to hydrogen, taking hydrogen as the reference point from which you measure every other masses. Note one thing. I want to explain something crucial. Take note here. This one is very, very crucial. You will see it. Now, you see the new values now. These guys are now being like pompous, like now feeling like. So what will now happen here is that, now think about it this way. This man that was having 1 is not giving 4. And it's just 1 hydrogen, 1 person. So how many of this kind of man would have actually give you this 4, this new value 4? How many of it? So that is when it will be worth 4. Because if 1 person give you the actual value of 1, the actual value, the 4 person will give you the value of what? 4. So it means 4 person will give you the value of 4. Now, if you also come here, you see that K here is what? K here, constant, is equal to the value here is 4. I call it K. I will tell you the reason why I call it K later. Now, look at this one. If this one that was having 2 before, how many of them would have given you this 8? You will see that it's also what? 4. Because 4 of them would have given, since 1 gave you what? 2. 4 of them would have given you 8. Okay? You still see that K here is also what? Equal to 4. Now, if you also come here and say how many of these would have given you this 12, you also see that 4 of them would have given you what? 12. Which means K is equal to what? 4. Now you don't see that the number of them, the thing affects their number that will give you this value. The changes affect the number of them. Like you count them 1, 2, 3, 4, we give you this actual value. 1, 2, 3, 4, we give you this new value. 1, 2, 3, 4, we give you this new value. Okay, so you now see this is where the Avogadro's number. This number you are seeing here is what we call Avogadro's number today. Though this is not Avogadro's number. This is how we get Avogadro's number today. The Avogadro's number we are using. Look at Avogadro's number. Avogadro's number is 6.02 times 10 raised to power 23. This is Avogadro's number. So this is K in chemistry today. The reason why this one is very big is that we need more of 1, 2, 3 of hydrogen in real chemistry. We need more of it. This is a very, which means we need many hydrogen to give that 1 gram. That 1 gram that they now assign to hydrogen. We need many, this number of it to give that 1 gram. So the same thing we need for every, and this Avogadro's number is what relates to mole, the mole that we use today. This Avogadro's number is what relates to mole. So many of us do not understand the difference between mole and molecule. In our next video, after this particular class, I'm going to be talking about that. So I don't want to talk about that now, so that this video will not be too long. It's already being too long. So I will talk about that later. This is how, so this is Avogadro's number. That's the number, this number, the same thing, this number and this number. They are just like functioning the same way here. You know, I use this one to explain just as an example. So, but in chemistry, this number represents this 4 that we have here. This number. This is what we call Avogadro's number today in chemistry. Okay, so that is why they tell you the Avogadro's number for 1 mole, and any substance, and this is what we call a mole. A mole. A mole is a substance that contains this number of particles, number of atoms. If you count the substance and it contains this number of atoms, it is called a mole. So you see how the reason why it is called, how we got this value. See, they are constant, irrespective of their sizes. The numbers are constant because they were measured with taking reference from what? The smallest unit. So we are done with this to illustrate the. We have used something to use this to illustrate the meaning of relative mass, how we got the relative masses of substances. Now, look at how in chemistry, since you have already understand this now, I want to go back to chemistry now to explain what it means in chemistry. Now, the actual mass of hydrogen, which is the reference point, is what? 1.67 times 10 raised to power what? Minus 24. Now they now say let the mass of hydrogen now be what? 1. Okay? These are small as this mass, they now say let it be 1. Now, the mass of carbon, which is what? 1.99 times 10 raised to power what? Minus 23. The actual mass, this is the mass of 1 atom of carbon. What will you now give to it? S. Okay, if you do this, it will give you S is equal to, you cross the same thing we did that time. You cross, it will now be what? 1 times 1.99 times 10 raised to power what? Minus 23 all over 1.67 times 10 raised to power what? Minus 24. So when you do that, it will give you 11 point something. When you approximate it, it will give you 12 grams. So today, that's why we say the mass of carbon is equal to 12 grams. However, since you are using relative masses here, you will not put unit. Relative masses does not have unit, because if I have mass here, maybe I have gram here, I also have gram here. This gram will cancel this gram. So relative masses does not have unit. So if you want to also calculate for, let me say, carbon, sorry, if you want to calculate for oxygen, you will also do the same thing with reference to the same carbon, with reference to hydrogen, sorry. So oxygen is 16 times heavier than what? Hydrogen. So that's what it means. The first one, carbon is 12 times heavier than hydrogen. this other one, oxygen, is 16 times heavier than what? Hydrogen. Since they were measured relatively to hydrogen. Let me divide this to know the actual value. 2.66 divide 1.67. That's approximately 16. We are correct. So that is what it means. It is what approximately was 16 when you divide that. So we now see how relative masses. So if you want to also calculate other ones, you still know their actual masses from spectroscopy. You can go and browse it, check the theorems of their masses. So you can also calculate the mass, verify the mass of other masses, just as I verify these ones now. Now we are done with this number third one. The next one is carbon as the new standard for measuring standard point. Now, today we don't longer use hydrogen again as our reference point. Today we now use carbon as our reference point. The reason being that hydrogen is not stable, is not consistent. The masses of hydrogen is not consistent. Like, also another reason is that it's not common as per carbon. So today we use carbon as a reference point today. We use carbon as a reference point today. Now, if we use carbon today as a reference point, based on its stability, consistency in measurement, like if I measure it today, if I come tomorrow, it's almost the same thing. If I come next tomorrow to measure it, it's almost the same thing. So that's what I mean, that the measurement is consistent. Okay, so because of that, and you know carbon now is common around us. Okay, carbon is also common around us. So we now use carbon today. Now, if we now use carbon today, look at what happened. We use carbon today. Look at what happened. Carbon is not the lightest. Carbon is not the lightest. Hydrogen is the lightest. And mind you, you know from the beginning that we want all our value to be from 1 and above. So if we use carbon that is 12, if we use carbon now that is heavier than hydrogen, like that, use the mass like this, which is 1.99 times 10 raised to power minus 23. If we use this value today for carbon, you will see that it will be, hydrogen will not be less than 1. Because if we say let this mass now, this mass be 1. Let's take reference. Hydrogen will be less than 1. Helium will be less. Carbon is number 6. Hydrogen, helium, lithium, beryllium, boron, carbon, number 6. So all these one, that's number 5, number 4, number 3, number 1, which is hydrogen, helium, lithium, beryllium, boron, will be less than 1. Relative mass will be less than 1. So because of that, we now say let us divide this mass by 12. It will now give us 1.66 times 10 raised to power minus 24. So 1.66 times 10 raised to power minus 24. Or let me so it will be, the answer is 0.1658 times 10 raised to power minus 23 all over, okay, minus, yeah, this. So this is the answer. If you move this one here, so that move the decimal point here, it will now be 1.66 times 10 raised to power minus 24. Because you move this one here, this number will now change to 24. This is how you will now relate. This is the mass we now use today. This is the mass we now use today. So I can remove everything here now. I can remove everything here and put this number here. But I am not going to do that, so that you will understand your definition later. So if I remove this, what you have here now is the same thing as what you have here. So that is how we so if you are now using carbon, what will you now? If you are not using 12 carbon unit, maybe one 12 carbon unit. That's it. The same thing you were doing before. Let's calculate the mass of hydrogen and using carbon as a reference. If this 1 all over, do you know that what you also have here is the same thing as 1 times this? Is the same thing as 1 times this. Or you say 1 times 1 all over 12 times 9, 1.99 times 10 raised to the power what minus 23. It's also the same thing. What you have here is also the same thing. Okay, so that is why now if you want to what you learn, do not the same way you the same thing you did to hydrogen. You not say let this mass, this new mass that we just calculated now that I told you that is the same thing with this. Let it be what 1. So if you make it 1, then since you divided this large heavier carbon by 12 and gave it 1 value, therefore all these other elements that are below carbon will now step up more than 1. So because we already divide the mass here by 12. So what we now do, let's calculate for hydrogen. Hydrogen that have the mass of, let me see, hydrogen have the mass of 1.67 times 10 raised to the power minus 24 will now be what? S. So when you cross multiply this one, it will now give you what? Equal to 1 times 1.67 times 10 raised to the power what? Minus 24 all over 112 times 6. 1 all over 12 times 1.99 times 10 raised to the power what? Minus 23. So if you do this, it will not give you, so this thing you have here is the same thing as 1.67 times 10 raised to the power what? Minus 24 all over 0.66 times 10, 0.66 times 10 raised to power 10 raised to power minus 23. So if you move this one here, if you move this decimal point here, this one will not turn, it will not be what? It will not be, if you move the decimal point there, it will not be equal to, it will not be 1.67 times 10 raised to power minus 24 all over 1.66 times 10 raised to power minus 24 because you move the decimal point. So this one will cancel this one. So everything here will cancel out. You now have 1.67 divide 1.66. So 1.67 divide 1.66. Let's check the mass of hydrogen now. 1.67 divide 1.66 is equal to 1.006. 1.006. Now see 1.006. So this is now the new mass of hydrogen. So it might be different from what you have in your textbook. Maybe it's calculator error. I don't know. So it might be better. It's above 1. That is what we just want to see. It's above 1. So this is now the new mass of hydrogen that was formerly taken as the reference point. Now carbon is not taken as the reference point. Hydrogen is now what? 1.006. This is relative mass. You now see it. Now look at how the definitions were. This definition, people now define relative masses. Now I want to give you the definition. They will say, what is relative mass? The formula comes, how the formula come about, the like formula. Now say relative mass of a substance is equal to the mass, the unit mass is equal to the unit mass of that substance all over 1/12 the mass of one carbon, mass of one carbon at the mass of 112, the mass of carbon 12, one atom of carbon 12, one per 112, the mass of one atom of carbon 12 of carbon 12. Let me clean here. Of carbon what? 12. So this is how they give you in your textbook. They say it is the unit mass of that substance. Why? I will tell you why I use substance here. I will explain later. It is the unit mass of that substance. 112, the mass of one atom of carbon 12. That is how they calculate, they define relative mass. Now, they got it from here. So formula are got, all formulas you ever think about, got it from real life situation, the actual situation. Look at it. This is what we are looking for. They want this formula to calculate for relative mass. So we want to calculate the relative mass of that substance. So to calculate it, it is the actual mass of that substance, which is we want to calculate the relative mass of hydrogen. This is the actual mass of hydrogen. Per 112, that of carbon, of isotope 12. Okay, carbon 12. This 12 here just means isotope. Just to identify the type of carbon we are talking about. We have carbon 12, we have carbon 13. It's just to identify the type of carbon. This one is what talks about mass. This one is not actually. This one is just for identity, to know the type of what carbon we are talking about. Like I told you before, we talk about isotope. Now, from here you can now calculate the relative mass of. Now we have at this point, I would like to tell you that we have, instead of using substance, we can say relative atomic mass. Relative atomic mass. We can say relative molecular mass. We can say relative formula mass. We can say relative proton mass. We can say relative neutron mass. So every mass you see in chemistry today are relative masses, not the actual masses. So if I say what is relative atomic mass, in case you ask, relative atomic mass is the mass of a unit, if the mass of one atom of that substance is the mass of one atom of that substance per 112, 1 all over 12, the mass of one atom of carbon 12. Now, if I say, you hear me, it is the mass of one atom of that substance per 112, the mass of one atom of carbon 12. Now, relative molecular mass, it is the mass of one molecule, not atom again, molecule of that substance per 112, the mass of one atom of carbon 12. If I say what is relative formula mass, the reason why I use formula mass here, because most substances are not atom, they are not molecule, they are just, some substances are ionic compounds. So this is a general umbrella for everything, but I just want to add every other thing to it. So formula mass, what is formula mass? It is the mass of one formula unit per 112, the mass of one atom of carbon 12. Then if they say what is relative proton mass, or the relative mass of proton, it is the mass of one proton per 112, the mass of that, per 112, the mass of one atom of carbon 12. What is the relative neutron of a mass? That is the mass of neutron. It is the mass of that. It is the mass of one neutron per 112, the mass of one atom of carbon 12. So this is how you calculate. So somebody would told you the mass of proton is 1. That is not actually the mass of proton. That is the relative mass of proton. You already see how we got the relative masses now. So somebody will tell you the mass of neutron is 1. The mass of neutron is the mass of one neutron is not 1. The mass of one neutron that one is a relative mass of neutron. So the mass of one neutron is very, very small, very, very small, just like hydrogen. Very, very, very small, almost the same thing as hydrogen, the same thing with proton. So that is how we. So the essence of this class now, we are done with the class. You now get to know. You now have the mindset of actual mass, relative mass. So when they are talking about actual mass now, you know what it means. When they are talking about relative mass, you know what it means. So put that in your mind. The next topic we are going to be treating in chemistry is mole. We are going to be unveiling something there again. So make sure you subscribe to my page, because like I told you, we are going to be unveiling many truths on this page. Make sure you don't miss out. Thank you. Bye.